Last time we talked about the contributions to binding, and specifically we talked about the contributions to the delta H in delta G equals delta H minus T delta S. In other words, the sticking or bonding, quote unquote, that causes binding. So these are the direct mechanical things that actually cause one molecule to stick to another. And we saw, just to summarize a little bit, that a lot of these interactions can be strong. The electrostatic interactions are very strong. The H bonding is very strong. Desolvation energy is a big term. But that they tend to be balanced all the time. So either by the fact that you have to get water away, and taking the water away costs you a lot of energy, or the fact that water, for example, H bonds pretty much as well as most of the biomolecules we're talking about, when you got to break a bunch of H bonds in order to form new H bonds between the binding partners. And so, even though these are nominally big contributions, big effects, they may not be big and they may not even be favorable. They can be unfavorable. If they are unfavorable, they're usually not hugely unfavorable, but unfavorable means, or even just weakly favorable, means that something else is usually responsible for the binding. And that something else, of course, the only other possibility is entropic effects. So we talked about 5 enthalpic effects. Now we're going to talk about 5 entropic effects. And like I say, most of the time, the binding is mainly due to these entropic effects. And so understanding them, these more subtle kinds of effects, not just mechanical sticking, but entropy processes, entropic processes, is really important to get any idea at all why most biomolecules, why most binding reactions in biology go at all. All right, first of all, so let's just go down them quickly here. There's the hydrophobic effect. We've talked about that a little bit. We'll talk about it more below. There's the fact that when you bring two biomolecules together, oftentimes there's bound water on coating both of those surfaces. You got to release that water. That's favorable. That causes bound molecules to become released. Translational changes, that's often unfavorable, well, at least as far as the molecules themselves are concerned rather than the water. Rotational changes, and then configurational changes within the molecules themselves. Most of these last 3 especially, are pretty straightforward, but these first 2 are a little less so, especially the hydrophobic effect. So let's talk about them. All right, first of all, the hydrophobic effect works something like this. You've got a bunch of water molecules. They're all hydrogen bonded to each other. And that means, and if you look around any one of these water molecules, the environment is statistically the same in all directions. That means you're just as likely to get good hydrogen bonding in this direction as you are in any other direction, which means that the water molecules have their full complement of rotational degrees of freedom, rotational states available to them. Now put a hydrophobic molecule, a non-polar molecule in there, or any other thing, a droplet of oil or a plastic surface, anything hydrophobic. Now when the water molecules, now things are not uniform in all directions anymore, right? There's one direction in which the water molecules can't hydrogen bond anymore. That means that they're fine hydrogen bonding in this range of angles, but anything outside that range of angles is going to be less favored because hydrogen bonds are important, right? If you can't form your hydrogen bonds, that costs a lot of energy. That means states without hydrogen bonds are going to be rare. That means almost all the time the molecule is going to be turned in a direction that allows it to form its hydrogen bonds, and the fact that one of those directions or some subset of directions can't form hydrogen bonds means that this molecule is rotationally constrained. We talked a little bit in the past about the role of hydrogen bonds in forming complexes between ligand molecules, drugs, and so on, and the binding sites on proteins. And I showed this exact slide, in fact, before, so this is from the HMG-CoA reductase part we talked about earlier. And yeah, the hydrogen bonds in the bound molecule get replaced by hydrogen bonds to water when the ligand isn't present, and likewise the hydrogen bonds to the ligand get replaced by hydrogen bonds to water. But that's not true for the hydrophobic parts. The hydrophobic parts have a very unfavorable interaction with water for the reasons given up above. They restrict the rotational degrees of freedom to the water. But when you take those things out of the watery environment and put them into a less watery protein binding site environment, then the water gets excluded from all these areas and goes out into the bulk where its rotational freedom is as high as it ever was. You've basically taken away the interface between the water and the hydrophobic whatever. And it's that interface between the hydrophobic and surface and the water that costs energy. We'll talk a bit more about that idea, the idea that there's an area of interface between a hydrophobic region and the water, and that interface is basically a high energy feature. We'll talk about that below. All right. Let's just look at another example of that kind of thing happening. Here is another molecule that binds substrates. This is the ABL kinase. It's implicated in cancer. It's an oncogene. When this guy gets turned on, he starts, it's a tyrosine kinase. It starts phosphorylating things. That's a signal which gives rise to a cascade of other signals that eventually causes cell division or cell proliferation. And that can happen in an uncontrolled way. That causes the growth of cancer. And so turning off the tyrosine kinase is something that a lot of anti-cancer drugs try to do. So that one of the things that a tyrosine kinase binds is ATP, because a kinase phosphorylates things and it uses ATP as the source of its phosphates. And it has a binding pocket that has, in this case, 3 different hydrogen bonds. It also has a hydrophobic region, and then it's got some exposure to water as well. Here is an inhibitor molecule that's fairly widely used. It's called imatinib, or Gleevec, as it's more popularly known. And it also has some hydrogen bonding opportunities, but only 2. Notice 3 on the actual substrate, only 2 hydrogen bonds in Gleevec. And that doesn't seem to cause too much trouble for the reasons that I've given above. Hydrogen bonds in the water get replaced by hydrogen bonds in the binding site, and so the number of hydrogen bonds determines specificity more than they do binding strength. On the other hand, this hydrophobic region hits a really hydrophobic region in the Gleevec. Notice that over here, nothing on this ATP is really very hydrophobic, so the fact that this hydrophobic region is here isn't really being used very much or very strongly by the natural binding process. The designers of this drug made heavy use of that hydrophobic property, hydrophobic pocket, by putting a really hydrophobic region onto the inhibitor Gleevec. So the H bonding, the sticking, the delta H contribution for Gleevec is actually worse than for the natural substrate. And remember that a drug like this, an inhibitor like this, has to bind stronger than the natural substrate, because otherwise the natural substrate will displace the drug. You have to bind stronger so that you displace the natural substrate. And in this case, the delta H, the enthalpic contribution, the binding is actually worse in Gleevec. It doesn't explain its high affinity. But on the other hand, it has this nice hydrophobic effect and therefore it has a much stronger hydrophobic effect contribution to delta G, or entropic contribution to delta G. And that's the explanation for the strong binding by Gleevec to this particular pocket. All right. The hydrophobic effect has been modeled experimentally, well, not experimentally, well, experimentally too, and we'll talk about that here. But it's also been modeled in simulations, and that's where a fair amount of the interpretation that I gave above comes from. In other words, this business about water rotational states being reduced, that comes from simulations mostly, because you can see water rotation nicely in a simulation, whereas it's hard to see by an experimental method. But there is experimental evidence for the same kinds of picture, and it comes from a rather weird type of experiment, one that you wouldn't think was relevant at all at first glance. Here's the experiment. You start with some methane dissolved in water, and then you move that same methane to be dissolved in carbon tetrachloride. Carbon tetrachloride is, of course, very hydrophobic. Water is very hydrophilic. And then you look at the delta H and delta S values for that transfer process, that transfer of a very hydrophobic molecule, CH4, methane, from a polar environment to a nonpolar environment, and you find that the delta H contribution is actually unfavorable. In other words, the sticking, the delta H contributions between the CH4 and the water are actually stronger than the ones between CH4 and the CCl4. And that's partly because of water polarity. It might also be because the hydrogen bonding is a little better when there's no CH4 disrupting the hydrogen bonding network. It's not exactly clear what's causing this number. But it means that it's not that CCl4 sticks harder to the methane than the water does. The water, in fact, sticks a little bit harder than the CCl4 does. On the other hand, you look at the number for the entropy change, and it's big and favorable, big and positive. And these experimental numbers don't tell us where that entropy is coming from, but the interpretation above from the simulations is the very likely ultimate source of it. The overall net effect at 300 K isn't very big. There's almost no change in delta G in going from taking methane out of water and putting it in CCl4. But it is a little bit favorable, a little bit negative. And then this is the same numbers, but for a somewhat bigger molecule, propane. And again, the sticking is a little unfavorable to transfer into CCl4. But there's a great big reduction or increase in the number of quantum states or microstates available to the system, a great big increase in entropy. And notice that even though the sticking is about the same between those two, the increase in entropy is greater for the propane than it is for the methane. That's consistent with the idea that the methane has a certain surface area with the water, which is smaller than the propane, which has a bigger surface area with the water. And so it's consistent with the hydrophobic effect ideas that the amount of entropy change should be proportional to the surface area of contact between the water and the molecule. All right. Here's that same experiment just shown a little bit more graphically. Let me make this a little bit smaller so we can see everything. You start out with two things, right? Everything on this side is the initial state of things. So you have a methane molecule in water, and yes, right in the area around the methane, there's restricted rotation for the water. But you also in the initial state here, you have some carbon tetrachloride, because we're going to transfer from one to the other, right? So this one's got the water's got the methane at the beginning, but after the reaction, it's the carbon tetrachloride that's got the methane. And what happens when the methane moves then from the water to the carbon tetrachloride? Well, two things happen really. One is you lose all the interactions between the methane that was in the water to begin with, and now you gain new interactions between the methane and the carbon tetrachloride. And what the delta H values we saw down below are saying is that that isn't a great big effect one way or the other. In fact, it's a little unfavorable. The actual sticking interactions are a little bit stronger in the water than they were in the carbon tetrachloride. The other thing that happened, and then of course, in the carbon tetrachloride case down here, the carbon tetrachlorides don't change their rotational entropy when the methane gets introduced. There's no hydrogen bonds in carbon tetrachloride. This guy has just as much rotational freedom after putting the methane in as he had before, whereas the water molecules up here gained a bunch of rotational freedom because they don't have this interface with the hydrophobic surface anymore. The other thing that happens, and we haven't talked about this before, but you'll see it in the calculations if you ever look into literature on this, and that is that notice another thing is happening, and that is that when the methane leaves the water collapses in and fills in this cavity. So there's a cavity formed here. And it costs a certain amount of energy to open up that cavity. If we were going back this way, it would cost a certain amount of energy to open up that cavity, and that means going this way, we gain a little bit of energy by allowing the cavity to collapse again. By the same token, though, going from here to here, going from the pure carbon tetrachloride to the methane dissolved carbon tetrachloride, you have to open a cavity in the CCl4, and that also costs some energy. Those energies are kind of a wash. What you cost down here, you gained up here, so there isn't very much net effect from the cavity formation, at least not in this case, but there can be. So I mostly just mention it for completeness. The main effect, the main real change that's driving these reactions is the change in water rotational entropy, or so we believe. I mean, the truth is that all these kinds of things are complicated. There's a whole bunch of little contributions in addition to the main one, but the biggest single one is the water rotational entropy. All right. I want to say a little bit more now about the hydrophobic effect because it's really important in biology. It drives protein folding, it drives the formation of DNA, it drives binding between two protein molecules, binding between DNA and a protein, binding between ligands and protein. A whole huge amount of biology is only possible because of the driving force produced by the hydrophobic effect. So let's say just a little bit more about it before we pass on to other topics. And this is not in your book, I don't think, or maybe I don't remember if it's in your book or not, but we can quantify the size of the hydrophobic effect in the following way. Let's suppose I've got a hydrophobic molecule like this one, and I roll a water molecule over its surface. Then that describes what's called the solvent exposed surface here. That's the surface of the molecule that's touching water. On the other hand, as I'm rolling these water molecules, let's suppose I keep track of the center of the water molecule. That gives me this surface. And that surface is the solvent accessible surface area, or SASA. And according to what I said above, the strength or the size of the hydrophobic effect ought to be proportional, or roughly proportional anyway, to the size of this solvent accessible surface area. And here's the actual relationship. It's very simple. Here's the delta G due to the hydrophobic effect. Let's call it HPE for now. It's equal to the size of the solvent accessible surface area, the SASA, times a quantity called the surface tension, which is a free energy per unit surface area. So free energy per area times area gives you free energy. That makes sense. What is this surface tension? Well, it's the same thing you've heard of many times before. It's the same thing, for example, that causes surface tension effects with water. In this case, it's a different type of interface. It's the energy associated with an interface. In this case, it's a different type of interface. It's not an air-water interface. It's a molecule-water interface or a hydrophobic area water interface. And there's an interface, a similar interface all around every molecule that's immersed in water, like, for example, a big protein. If we look at the amino acids, you can also define the surface areas associated with those amino acids. And you can assign a certain amount of solvent accessible surface to each part of each amino acid. And when you put all these amino acids into a protein, that allows you to point by point, atom by atom, residue by residue, assign a certain value to this surface tension to every part of every amino acid on the protein, and in that way calculate how much effect the hydrophobic effect is having on any given binding process. And in molecular simulations, that's exactly what lots of programs do. All right, that is enough about the hydrophobic effect. Now let's go to the next contribution. Actually, let's see. There is another contribution that we skipped over here. Oh, that's the release of water thing. I guess we'll come to that next. These slides are a little out of order, sorry. The next contribution we're going to talk about anyway, let's see, where's there's the water release part down there. The next contribution then is the loss or gain of translational entropy, rotational entropy, and internal configurational entropy. And this is pretty straightforward. There isn't too much to talk about. I think it's what everybody would have assigned to a delta S for binding anyway, naively ignoring hydrophobic effects and all the other things. This is the one it's perhaps the most obvious if you've got two molecules to start with. They each have X, Y, and Z degrees of freedom, and that means entropy associated with each of those degrees of freedom. When you put them together into one molecule, there's only one set of X, Y, and Z degrees of freedom, not two. Or there's three sets of variables and not six, maybe a better way to put it. And so there's been a loss of translational degrees of freedom and therefore a loss of translational entropy. Of course, that can be compensated by other effects, by hydrophobic effects, by water release effects, and so on. This is not the only contribution, but it is a contribution, and it's a pretty much I don't see any way that it can't be anything but unfavorable. This loss of translational entropy, when a molecule binds, has to be unfavorable. Likewise, the original molecules can rotate, and they have three rotational degrees of freedom, three angles in which they can rotate. And there's two molecules, so there's 6 angles altogether. But after they come together into one complex, then there's only 3 degrees of freedom left. And so there's been a loss of rotational entropy as well, and that also has to be unfavorable. And we'll see below that this is the biggest one. The translations are the biggest contribution. The rotations are the next biggest, but there's a third one, and that's the fact that if I have some molecule that's got some internal degrees of freedom, it can flop around a bit, and you bind it to a binding pocket, well, it can still wiggle a little bit, but a lot of its floppiness has been restricted, and that also represents a big loss in degrees of freedom and in microstates, quantum microstates associated with those degrees of freedom, and therefore a loss of, I call it internal rotation delta S, but generally it's a restriction of the configurational freedom, whether it's rotation or something else, in the molecule when it binds. Again, let me say that a lot of times when the molecule binds, it can still wiggle around on here. It just can't wiggle as much. And so how big this effect is depends on exactly how tightly it's bound and exactly the way it binds and so on. And the same thing can happen on the protein itself. There are side chains in the amino acids on the protein that also get their freedom restricted. And so how big it is kind of hard to tell just by looking at a structure, say. But it's good to keep in mind that this is also a contribution and also there and also has to be taken into account. All right, here are some numbers. I think these come from simulations. I I don't know this guy, so I'm not sure if it's a simulation or not. It probably is a simulation, though, because I'm not sure exactly how these kinds of things would be measured experimentally. Maybe there's some clever experiment to do it, but I think this is probably a simulation. And they assign an actual entropy change due to a loss of translational entropy by a small molecule. For a big molecule like a protein, this number will be bigger. But even for a small molecule, it's a pretty big contribution, a pretty big entropy change. And if you lose it, it's a negative entropy change. If you gain it, it's a positive entropy change. So water molecules, for example, are small molecules. Every single one of them that gets released, let's say, upon binding is gaining that much entropy or something like that much entropy. On the other hand, whenever a ligand and a protein come together, you're losing this much entropy. And that entropy change can be converted into a delta G change, if you want to think in terms of delta Gs, which is often what people do, by using delta H minus T delta S, right, where the delta H is 0. So it's just the T delta S term, and that works out to be roughly 40 kilojoules per mole. Not a small contribution, enough to, I mean, it's way bigger than RT, right? RT is only 2.5 kilojoules per mole. This is much bigger than that, so it's enough to cause pretty strong binding all by itself. Rotational entropy, on the other hand, also has a pretty big contribution. It's not as big as the translations, but it's still significant. Roughly 25 kilojoules per mole when you turn it into a delta G. And the internal degrees of freedom, so rotation around internal bonds per internal bond. So if you start with a free bond, a single bond rotation, let's say, which can spin freely, and then you go after binding to a situation where the bond can't rotate at all, that's the maximum possible loss of entropy, then that's 12 to 20 joules per mole per degree Kelvin, and about 5 kilojoules per mole in delta G. And I say here that all these are significant, especially the fact that, I mean, the configurational entropy per bond is relatively small, only 5. But there can be a dozen bonds, or there can be, a whole bunch of bonds, and then this rotational contribution can be a great big effect. It can be bigger than the other two. All right, so that's an entropic contribution due, this is sort of the intrinsic part of binding, right? These are consequences of the mere fact that you're turning two molecules into one at all. And so you always have these contributions. On the other hand, the last one we're going to talk about is what I've mentioned several times in the past, namely that if I have, for example, a protein that's binding to a ligand, there can be water molecules on the ligand too, for that matter. When the two come together, very often there's not enough room left for the water molecules to stay. They have to get kicked out. They were more or less immobile to start with. I mean, I have to say, these water molecules aren't necessarily strictly bound. They can be only partially bound. So they were partially free to start with, which means that when they become completely free after the ligand binds, it isn't like you're releasing an entire water molecule. So this can look like a bigger effect than it really is, because you aren't fully releasing the molecules. They were already kind of half released even before. But still, if you can release several water molecules as a result of binding, that's a big favorable entropic effect. If you look at the crystal structure for a lot of proteins, you'll see something like this. The gray stuff here, the ribbon image is for the protein, and all these red guys are water molecules that showed up in the crystal structure. The fact that they show up means they're not mobile. You only see mobile things in crystal structures and by X-ray crystallography. You only see immobile things by X-ray crystallography. So these water molecules were all stuck hard enough to show up as water molecules in a crystal structure, and that means that they're, well, maybe not strictly really hard bound, but they're not free either. Their translational, rotational degrees of freedom are pretty severely restricted. And the evidence for that is that they show up at all, that you can see them at all in a crystal structure. Here's one of the reasons why these guys get stuck is you've got a water molecule here, there's an acceptor over here, there's an acceptor over here, and there's two donors on the water molecule, so it bridges across between two acceptors. That's one way that a water molecule, I mean, there's lots of acceptors on any protein. The whole backbone of the protein has got all kinds of acceptor sites on it, so waters can stick all over the protein. That's a big part of the reason why the protein's soluble in water at all, in fact. And so you got lots of sites like this. You can see from this picture where the water molecule is bound by its hydrogen bonds to two acceptor sites on the protein. All right, here is, we looked at this picture before. We were looking at the electrostatic contributions in that case. We skipped this other contribution, which is that they've kept track of here. This is a simulation for sure. Yeah, let's see, yeah, Barry Honig here is a simulator guy. So this is a simulation for sure. And I mean, there's many different things you can get from a simulation, but they've broken out the electrostatic contributions, and then they've broken out this total buried surface area, interface area. So in other words, it's the amount of area of contact between the two guys when the two proteins come together. And then they further refine that to look at just the surface area that's due to hydrophobic side chains. In other words, how much hydrophobic surface is getting moved away from the water, is getting excluded from the water, is getting buried. That's a measure of how favorable the hydrophobic effect will be for these molecules. And they don't put a free energy number on these, they just give numbers for the amount of area, but these are considerable areas, right? These are angstrom squared areas. 200 angstrom squared, that's an area, what about 15 by 15, 15 by 20, something like that. So that's a 15 by angstrom area by a 20 angstrom area that got buried when those two molecules came together. That's a lot of hydrophobic surface that's been buried. Even bigger here, almost 650, almost 600 there, almost 300 here. So a lot of surface area is getting buried. And on the other hand, if you look at the electrostatic contributions, we did this before, the electrostatic contributions are even unfavorable in 3 of the 4 cases, despite the fact that these are very strong binding constants. So the binding constant is not explained by these electrostatic interactions, and very likely it is explained by these very large hydrophobic surface areas that are buried. Is there anything else I want to say? I guess it talks about pattern matching, or I have something written here about pattern matching. That has more to do with the electrostatic effect than the hydrophobic effect, though pattern matching for hydrophobic effect also occurs. That goes to specificity. In other words, why doesn't every protein stick to every other protein? Why does one protein stick only to one other protein amongst 1,000 other possible targets? That's specificity, and has to do with pattern matching, as you can imagine. When the hydrophobic patches and the electrostatic patches and the hydrogen bonding opportunities all line up, then you get strong binding. If they don't line up, then you don't get binding. And that specificity, we'll talk about that next. That's chapter 13. That will be the topic of our next lecture.